In this lecture, we will work out various examples on second-order circuits. Our first example is a parallel RLC circuit. And the source is of impulsive nature, 8 delta t minus 3 amps. The initial conditions are 0. Vc0 equals 0. Okay. And what else? We're given that Vc 3 plus, that is just after these impulse affects the circuit, is given to be 1 volt, and the response, we're told, is critically damped. Is critically damped, and we're asked for determine the inductance and the capacitance of dynamic components, determine L and C, and find the capacitor voltage for T positive for future times. Okay, so let's begin our analysis, and we can divide our analysis into 3 parts. The first part is between time T equals 0 and 3 minus, just this guy becomes active, okay. And actually there's nothing to analyze there because the initial conditions are 0 and the source does nothing during that interval, so everything remains 0, okay, for that interval from 0 to 3 minus. And then we're going to make the analysis for the infinitesimal interval from 3 minus to 3 plus, okay. And we're going to see how the impulsive current source changes the initial conditions. Okay, in fact, we're given that we're going to figure out by that change of initial conditions, initial conditions, we're going to determine the inductance and the capacitance, and then with our new initial conditions, we're going to figure out the evolution of the circuit starting from t equals 3 plus to the future. Okay. So between time t equals 0 and 3, initial conditions are 0, the source provides 0 amps, therefore this is an open circuit, so the circuit is dead. Okay, nothing happens, everything is 0. Therefore, there is nothing to compute really. Capacitor voltage is 0. Throughout this interval. And then between 3 minus and 3 plus, let's figure out how the initial conditions change. For that, what we do is we have to figure out the impulsive component of the inductor voltage and the impulsive component of the capacitor current, so that using the term equation, by integrating those variables, we can figure out what happens at t equals 3 plus to inductor current and capacitor voltage. So this is our source, t minus 3 amps. Here we have the resistor. Here we have the inductor. Okay. And here we have our capacitor. Okay. Plus minus VL, and this is IC. Now we say that inductor current remains bounded, and to figure out the impulsive component of the inductor voltage, what we do, we replace inductor using substitution theorem by any bounded current source. Okay, And since it doesn't matter what bounded current source you choose, we always choose the simplest one, which is the current source that provides 0 amps. So that makes an open circuit for the inductor. And the dual case is true for the capacitor. And for that reason, we replace the capacitor with the short circuit. Now, once you do that, it's clear that BL is 0, okay? Or the bound component of the inductor voltage is 0, therefore inductor will not experience any jump at t equals 3. Okay. As for the capacitor current, all this current will be flowing over the capacitor, and that would create a jump, a discontinuity at the capacitor voltage. And that discontinuity is given. Okay, so from Vc equals 0, it jumps to Vc equals 1 volt. Okay, and using that information, we will be able to figure out the capacitance for the capacitor. So ICT, capacitor current is 8 delta T minus 3 amps. Okay. Therefore, Vc 3 plus equals Vc 3 minus plus 1 over C 3 minus 3 plus 8 delta T minus 3 dt. Okay. Now, this is given to be 1, this is 0, because Vc 0 equals 0 and nothing happens in this interval from 0 to 3 minus. Therefore, Vc 3 minus is also 0. And this here, by definition, is 8, the definition of the impulse function. So what we have is 1 equals 8 over C. Which tells us that the capacitance must be 8 farads. Okay, C must be 8 farads. Now let's figure out the response for t greater than 3 and also the inductance value L. Okay, for t positive, what we have is, starting from t equals 3 plus to the future, this is just 0, therefore we can replace the current source with open circuit. In other words, we can just take out of the circuit, and the circuit then becomes a homogeneous parallel RLC circuit. Okay, so we have the following topology for t greater than 3. We can now forget about the independent source. This is 1 ohm L by L. This is the capacitor voltage Vc. Now we have figured out the capacitance, which is 8 farads. How about initial conditions? Vc 3 plus 1 volt and IL 3 plus equals, well, we said that the inductor voltage is 0, or the positive component of inductor voltage is 0. Therefore, if you integrate that, you will have nothing, okay, for the inductor. That means inductor experiences no jump. Therefore, IL 3 plus equals IL 3 minus, which is 0 amps. Okay, so this is a parallel RLC circuit. We can write the differential equation immediately. E squared Vc plus 1 over Rc dVc plus 1 over Lc Vc equals 0. The right hand side is 0 because we have no source in the circuit. So that yields d squared Vc plus 1 over 8 dVc plus 1 over 8 L Vc, okay, equals 0. Hence, the characteristic polynomial of the circuit is, well, can be determined by looking at the coefficients of the left-hand side in our differential equation. Namely, characteristic polynomial reads s squared plus 1 over 8s plus 1 over 8l. Okay. And that equals, okay, we don't know what that equals exactly, but what we know is that the response is critically damped. And by definition, it means that the natural frequencies, namely the roots of the characteristic polynomial, are repeated. Hence, this must equal s plus something squared, okay, by definition. So both natural frequencies are at minus alpha. So if you write this in open form, 2 alpha s plus alpha squared, this polynomial and this polynomial, they must be equal, and that immediately tells us what alpha should be. Okay, 2 alpha is 1 over 8, therefore alpha is 1 over 16. And then, using that, we can figure out alpha squared, and alpha squared must equal 1 over 8l, and from there, we can figure out inductance. Okay, so 2 alpha equals 1 over 8. Okay, hence alpha equals 1 over 16. And then 1 over 8l equals alpha squared. Alpha is now computed 1 over 16, therefore this must equal 1 over 256, therefore 8l equals 256, meaning that inductance must be 32 henries. Now we have figured out the circuit parameters, capacitance 8 farad and inductance 32 henries. Okay, now what remains is to figure out Vc for t greater or equal to, t larger than 3. For that, we have everything we need. We have the differential equation, or we have the natural frequencies, and also we have the initial conditions. Therefore, let's write down the solution. D squared Vc plus 1 over 8 dVc plus 1 over 256 Vc equals 0. So that's the differential equation describing the evolution of capacitor voltage. Vc initial condition, Vc3 equals 1 volt. Okay. And dVc3 initial condition for the rate of change of the capacitor voltage is what? So that equals 1 over C times IC, okay, using the terminal equation of the capacitor. That equals 1 over 8 times, no, that IR plus IL plus IC equals 0 by KCL. Therefore IC you can write as minus IL3 minus IR, the resistive current. And resistive current is resistive voltage divided by resistance, and resistive voltage is no other than the capacitor. Excuse me, resistive voltage is no other than the capacitor voltage divided by resistance 1. Okay. Now this is 0, this is Vc3 is 1, therefore we can figure out the Vc3. Which yields minus 1 over 8 volts per second. Okay. So, to sum up, we have the characteristic polynomial v of s equals s plus 1 over 16 squared. Okay, because alpha is 1 over 16. And natural frequencies S1, 2 are both at minus 1 over 16. Therefore, VCT, or the form of VCT, reads as follows: equals K1 plus K2 T times e to the minus t over 16. Okay, we can write that, but since the initial condition is, initial time, now we're considering as 3, so it's easier to deal with VCT if you write it in this form. T minus 3, because 3 is now our new initial time, times e to the minus t minus 3 over 16. Okay? And using the initial conditions, VC3 equals 1 and dVC3 equals minus 1 over 8, we will figure out the two unknowns in the homogeneous solution, K1 and K2. Okay. VC3 equals 1, dVC3 equals minus 1 over 8. Okay. For that, VCT yields K1 equals 1 and K2 equals minus 1 over 16. Hence we can write VCT equals 1 minus 1 over 16 t minus 3. So this is our polynomial being multiplied by the exponential term e to the minus 1 over 16 t minus 3 volts. Okay. For t greater than 3. Okay. And for earlier times, everything is 0. So VC is 0. Okay. It goes at 0. And then what happens is at t equals 3, due to the impulsive current source, it jumps to 1 volt. And from 1 volt at t equals 3, what's going to happen is it's decaying toward 0 as time goes on. Note that this t term is increasing as time goes on, but exponential function always dominates any order of polynomial eventually. Therefore, the overall response should converge to 0 as time goes to infinity. Okay, now we're ready for our next example. This time, we'll consider a series RLC circuit. Plus minus, so yes, the input to the circuit and parameter values are given as 1 over 8 henries and 0.5 farads. The direction of the inductor current is given as follows, and capacitor voltage polarity is as such, plus minus. Now, we're given the following information. VC0 minus is minus 3 volt, so that's initial capacitor voltage. Initial inductor current is 0, so therefore initially there is no stored energy in the inductor. And as for the input to the circuit, the waveform for the voltage Vs is provided as shown, Vs volt 0. So it's constant for 30 seconds, okay, at magnitude 15. Okay. So for the initial 30 seconds, this source is providing 15 volts fixed. And then it drops to 0. Okay, therefore, the circuit now becomes homogeneous for a while. And then at some later time, we have applied to the circuit from the input an impulse function, okay, impulse wave at 55th second. And what we're asking for is VCT for t greater than or equal to 0 for future times. Okay, so let's write down what we know about the circuit and then we can begin our analysis. Let's first write the differential equation, which we know by this time by heart. It's a series, classic standard series RLC circuit. Therefore, the differential equation is plus R over L BC plus 1 over LC BC equals 1 over LC BS. Okay, so that's the differential equation. And for the parameter values given, this boils down to d squared BS plus R over L makes 10 dBs plus 1 over LC, that makes 16. Excuse me, this is VC. 60 VC equals 60 Vs. Okay. This is in terms of capacitor voltage, which is fine because we're trying to figure out the capacitor voltage. So we need to keep at initial conditions in terms of capacitor voltage and the rate of change of capacitor voltage. VC0 minus is minus 3 volts and dVC0 minus the initial condition for the rate of change of capacitor is by the terminal equation. This equals IC divided by C, the capacitance, and IC is same as IL, therefore this equals IL0 over C. IL0 over C. And that reads 0 because initial inductor current is 0. Okay. Now there are two approaches that you can tackle this problem. One is doing the region by region analysis. Okay, so what you do is first you figure out what happens from 0 to 30. Okay, the input is 15, you know the initial conditions, solve the differential equation, obtain a solution. And then at 30, the input disappears, so that means you have a new differential equation where the right hand side is 0. Figure out initial conditions at 30 and make analysis from 30 to 55 minus. Okay. And then at 55, the impulse affects the circuit, so that would mean certain changes, certain jumps in the capacitor voltage or the dynamic components variables. You figure out those jumps, and then that means you figure out your new initial conditions for the time t equals 55 plus, and from 55 plus to infinity, you make the last piece of your analysis. Okay, so that's one way. Another way is that we can use superposition because the circuit is LTI. Superposition of what? Superposition of zero state response and zero input response. Okay. First, you can kill the source, and for these initial conditions, you figure out VCT. Okay, put it in your pocket. So that's your zero input response, and then you set all the initial conditions to 0 because now we're going to figure out the zero state response and figure out the response for this waveform. Now, one way to figure out the response for this waveform is figure out the step response. Okay? If you know the step response, note that here we have a pulse which can be represented in terms of 2 steps, and here we have an impulse which can be represented by simply differentiating the step response. Therefore, if you know the step response for the circuit, then you can figure out the response of the circuit, zero state response of the circuit for this special input. And then we can, at the very end, combine zero state response and zero input response, which we can because the circuit is LTI. It allows superposition. So let's do the second way. Meaning that we begin with the zero input response. We ignore the input and just figure out the part of the response due to initial stored energies in our dynamic components only. Zero input response. Okay. let's call it V sub Zi T for the capacitor voltage. Now, d squared Vc plus 10 dVc plus 16 Vc equals 0. Now we kill the source, therefore the differential equation becomes homogeneous. Vc 0 minus 3 volts, dVc 0 is 0. Okay, so we need everything. Well, we have everything we need to arrive at VCT. Okay, first we have to figure out the form of capacitor voltage, and for that we have to determine the characteristic polynomial. ds equals s squared plus 10s plus 16, which can be written as s plus 2 times s plus 8. And when you write it in that form, it becomes obvious that we have two real distinct roots, one at -2, the other at -8. Therefore, the response will be overdamped by definition. And the form of the capacitor voltage, or the form of zero input response, looks like K1 e to the minus 2t plus K2 e to the minus 8t. Okay, the overdamped response. Now let's figure out K1 and K2, which we do by using the initial condition constraints. Vc0 minus 3, plugging t equals 0, and what remains must equal -3, so that yields K1 plus K2 equals -3. And then differentiate, and then plug in t equals 0. In that case, you have -2 K1 minus 8 K2 equals 0. Two equations, two unknowns. That yields K1 equals -4 and K2 equals 1. And our zero input response is now determined. Therefore, V0 input t equals -4 e to the -2t plus 8 e to the plus 1 times e to the minus 8t volts. Okay, so that's our zero input response. So to figure out the zero state response, we figure out first the step response, because we know that this waveform can be expressed using the step response, using the step function. Okay, step response of the circuit. Okay, let's call it S of t. D squared Vc plus 10 dVc plus 16 Vc equals 16 Vs. Now Vs is U of t. And by definition, initial conditions are 0, okay, for the step response. And then what we have is, because we have a non-zero right-hand side, we also have a particle solution. Particle solution in this case is constant, because step is constant for t positive, and the particle solution turns out to be 1, okay, which we determine directly using the differential equation. And homogeneous part of the solution is K3 to the minus 2t plus some other constant times e to the minus 8t. Okay, this homogeneous response we write by using the natural frequencies of the circuit, which we figured out from the previous part. Now, that natural frequencies depend on the characteristic polynomial. Characteristic polynomial depends on the left-hand side of the differential equation. Okay. Therefore, it's independent of what type of input you apply to the circuit. Okay. Hence, we can use the previous natural frequency information. So that's homogeneous solution. Therefore, the sum is the complete solution. VCT equals 1 plus K3 e to the minus 2t plus K4 e to the minus 8t is how the step response looks like. Now, let's figure out the let's figure out the K3 and K4. For that, we use the initial condition information. This input will not cause any jumps at the initial conditions. Therefore, what we have is VC0 plus equals 0 and dVC0 plus equals 0. Okay. Now, plug in t equals 0 and equate that to 0. So that yields 1 plus K3 plus K4 equals 0. And then differentiate, and then plug in t equals 0, and that yields minus 2 K3 minus 8 K4 equals 0. Two equations, two unknowns, and we can figure out the coefficients K3 and K4. K3 turns out to be minus 4 over 3, and K4 turns out to be 1/3. Okay. And then we have our solution. Step response is 1 plus, or 1 minus 4 over 3 e to the minus 2t plus 1/3 e to the minus 8t for t positive, and everything is 0 for t negative. Therefore, step response is 1 minus 4 over 3 e to the minus 2t plus 1/3 e to the minus 8t, and everything is multiplied by unit step. This tells us that this is what we have for t positive, and everything is 0 for t negative. Okay. Once we have step response, we can easily obtain the impulse response without looking at the circuit. All we have to do is, since the impulse function is the derivative of unit step, thanks to the fact that our circuit is LTI, the impulse response is the derivative of step response. Impulse response of the circuit. H of t simply is the derivative of step response. Step response is here, differentiated, and this is what we obtain. H of t equals 8 over 3 e to the minus 2t minus 8 over 3 e to the minus 8t ut. Okay, so that's the impulse response. Once we have step and impulse responses, we can now easily express the input waveform in the original question in terms of these two functions, s of t and h of t. So let's do that. And that will immediately give us the zero state response. VZST. So first, let's write Vs of t in terms of S of t and H of t. This was Vs of t. Okay. 30. This is 15. Vs t0, and then somewhere here we have an impulse at t equals 5 seconds. Therefore, Vs of t equals 15 u of t. Okay, so that means 0 for negative times, and from t equals 0 to the future, it's fixed at 15. But what happens is at 30 we drop to 0. So therefore we have to cancel the part of this waveform starting from t equals 30 to the future. So that means we have to subtract from this a delayed step with the same magnitude, minus 30. Okay, and then at t equals 55 we have an impulse with magnitude 3. Therefore we have to add that to complete the expression for Vs of t. Okay, t minus 55 volt. And that means the zero state response is, since circuit is LTI, this produces 15 ST, this produces 15 ST minus 30, and this produces 3H T minus 55, using homogeneity and time invariance. 15 ST minus 15 ST minus 30 plus 3H T minus 55. So that's the zero state response for the given input waveform. Finally, the overall response for the capacitor voltage simply is the sum of zero input response and zero state response. VZIT plus VZS. In our last example, final example, we're going to consider again a second order circuit, which is neither parallel nor series, but it can be reduced in some sense to one of those topologies. We'll see how. Okay. Example. This is our topology. The sources are constant. 6 volt. Inductor current 104 Henries. Capacitor voltage 103 farads. And these are the resistance values, 6 ohm and 3 ohm. Initial conditions are given as 9 volts for the capacitor voltage and no initial current on the inductor. Find the capacitor voltage VCT for future times for t greater than equal to 0. Okay. Now, here is, let's say, classical way, which is, well, derive the differential equation. Okay, using KCL, KVL, term equations in terms of the formulation variable, which in this case is capacitor voltage VC. Then obtain the initial conditions for that differential equation, namely obtain VC0 and dVC0. VC0 equals 9 volt. This is given. Then we also need dVC0. Okay, dVC0 is IC0 over C by the terminal equation of the capacitor, and then IC0 is this current. And this current equals 2 minus IL. IS0 minus IL0. Divided by capacitance C. IL0 equals 0. IS0 is 2. Therefore 2 over 1/3 is 6 volts per second. 6 volts per second is the initial rate of change for the capacitor voltage. Then you have the differential equation, you have the initial conditions, just figure out the solution. Solve for what you're asked, ECT. Okay. So that's a way, and it's doable, clearly, but there's another more practical, more engineering-oriented way, okay, to reach the solution. And let's briefly talk about that approach also. Here is another way. Find the natural frequencies of the circuit without obtaining a differential equation. How is that possible? First, for that we have to remember that natural frequencies, they come from the characteristic polynomial. Characteristic polynomial comes from the left-hand side of the differential equation. And the left-hand side of the differential equation is where we has nothing to do with the inputs, okay, which appear on the right-hand side. So to find, therefore, the characteristic polynomial, we can just kill all the sources, independent sources, all the inputs in the circuit, and then consider that possibly simpler topology. And then using that differential equation of that homogeneous topology, we can figure out the characteristic polynomial and consequently the natural frequencies. Okay, characteristic polynomial does not depend on the inputs. Okay. Therefore, we can attempt to compute them by killing the sources, hence kill the independent sources in the circuit. Okay. Now, if we kill these two sources, replacing this guy with an open circuit and this guy with a short circuit, this is what we have. CL, let's call this resistor R1 and this guy R2. The current source is killed, that is displaced by open circuit. The voltage source is killed, that means it's replaced by short circuit. Okay? So this circuit's natural frequencies and this circuit's natural frequencies are same. Now, one nice thing about this circuit is that it has a topology that we're already familiar with. If you replace this two resistors by the effective resistors, note that they appear in parallel, so we can do that. If you replace this by a single resistor, then everything becomes in series with one another, and we have the series RLC topology, for which we know the differential equation. Therefore, we can obtain natural frequencies easily by killing the sources for this example. So this yields series RLC topology, that is d of s, the characteristic polynomial equals s squared plus r over ls plus 1 over lc. Okay. This is r, where R equals the effective resistance, which we compute by parallel summing R1 and R2. So, for the parameter values given here, that makes d of s take the following form: s squared 8s plus 12. Okay. That means we have natural frequencies at -2 and -6. S12 equals -2 and -6. Okay, so the response will be over that two real roots, negative and distinct. Okay, then what? We also have to note the following. Notice that the sources are DC, meaning that they are constant. We have a constant current source and a constant voltage source. Hence, the right-hand side of our equation, differential equation, must be constant. Okay? Or the particle solution must be constant. Hence, the particle solution Vp will be constant. Okay. Now, the overall solution is particle solution plus the homogeneous solution. Homogeneous, we know the form of homogeneous solution is K1 e to the minus 2t plus K2 e to the minus 6t. And then we have the particle solution, which is constant. Let's call it A. So the overall solution is A plus that homogeneous solution. So let's write that down. VCT equals K1 e to the minus 2t plus K2 e to the minus 6t, homogeneous part, plus the particle solution, plus A. VPT. This is, once again, this is constant. Particle solution is constant because the right-hand side of our differential equation must be constant. And that we deduce from the fact that all the sources, all the inputs in the circuit are constant. So, even without knowing K1 and K2, we know something about the solution, and it's the following. As time goes on, no matter what K1 and K2 are, the homogeneous part will disappear. Okay, so this is EHT. So, at t equals infinity, the capacitor voltage becomes that constant, which we call the particle solution. So note that Vc infinity, or A equals Vc infinity. A must equal Vc infinity. Okay. Hence, we can figure out A by figuring out Vc infinity, and Vc infinity we can figure out by using the steady state circuit. Hence, check the steady state circuit. Okay, we're talking about DC steady state, which we can't talk about because the sources are constant, and we know that in DC steady state, every variable, every current and every voltage is constant throughout the circuit. So that one implication of that is that the capacitor behaves like an open circuit and the inductor behaves like a short circuit in DC steady state. And using that piece of very valuable information, we can easily compute the infinity values for capacitor voltage and inductor current. and 6 volts. This is IL infinity, and this is VC at infinity. 6 ohm, and this is 3 ohms. Okay. At T equals infinity, inductor current, inductor behaves like a short circuit because inductor voltage has to be 0. Okay. And likewise, the capacitor behaves like an open circuit because the capacitor current has to be 0. Why capacitor current has to be 0? Because IC equals CdVc. Okay, this is the terminal equation for the capacitor, and in DC steady state everything is constant, so that means capacitor voltage is constant. Okay, therefore its rate of change must be 0. That's what tell us that IC is 0. The capacitor current must be 0. Therefore, capacitor behaves like an open circuit. For the dual case, inductor behaves like a short circuit in DC steady state. Okay. Now, because this inductor is now short, this voltage and this voltage must be the same. So, capacitor voltage appears across the terminals of the 3 ohm resistor. Let's figure out VC. Okay, just write the known equation here. We have VC minus 6 over 6 plus VC over 3, this current, plus this current, which is, since it's open circuit, all this to end is flowing over this wire. In other words, IL infinity equals 2. Therefore, this current is minus 2. That equals 0. Okay, a single equation in terms of a single unknown, and that gives us that VC infinity must be 6 volts. Okay. And with that, we have now figured out the particular solution. What remains to be figured out further is K1 and K2, and for that we're going to use the initial condition construct. VC0 equals 9 volts and dVC0 equals 6 volts per second. So that's the last part of our analysis. Now we can write VCT equals K1 e to the minus 2t plus K2 e to the minus 8t plus the particular solution, which is VC infinity, which is 6. Okay, apply the initial condition constraints. Okay, to this overall solution. We have VC0 equals 9 volt. Plug in t equals 0, and that equate that to 9, so that means K1 plus K2 plus 6 equals 9. dVC0 equals 6 volt per second. Differentiated, plug in t equals 0, and we have minus 2 K1 minus 8 K2 equals 6. 2 equations, 2 unknowns. Okay. Give us the following values for K1 and K2. K1 equals 6 and K2 has to be minus 3. And we're done. Okay. Capacitor voltage for t greater than or equal to 0, therefore must be 6 e to the minus 2t minus 3 e to the minus 8t plus particular solution 6 volts.